Hi, hello, how are you? Craig Chapman here, and this is going to be a short show and tell about where I'm at now with my neural network experiments. Now, this is going to be the last video in this series, and I just wanted to show to you where I've got to with some of my experiment work. Now, we've got two tests here, two test programs, and these two test programs you've seen before in earlier parts in this series. However, in those parts, the neural networking code behind them wasn't exactly cleanly written. It was written more for educational purposes than anything else, and didn't follow the vector matrix math examples that I gave in my last two videos. And that's what I'm going to show you here today. Basically what I've done, I've created this math library here, this math package, which creates vectors and matrices as helper classes, or helper records rather. So if we take a look here, we have vector double, it's a record. It has local data and an engine buffer, which I'll explain in just a moment. And then it has operator overloads, allowing me to add vectors together, add vectors to doubles to scale them, and so on. And I also have this matrix double type, which allows me to do the same with matrices and to multiply matrices with vectors and so on. And then the code in the integer and single versions are pretty much the same. They just use a different data type. So single being the data type here, integer being an int32, and double being the double data type. And I do have plans to add a half precision floating point to this library also. Now what this library allows me to do is to create records of type vector double or vector single and instance them as vector types. So I'm going to create a new project here just to show you that working. I'm going to add a new project, a console application, and I'm going to set the path to find my units. So I'm going to go ahead up here, search path, and let's browse and find my source code, which is in here, and then I want to add the platform and configuration piece to the end of this. Okay, so now I should be able to find my math library with this project. What I should be able to do is, if I use this d.math, that's my math library, then I can have a type, let's say a vector, we'll call this v1, vector single, we'll have v2 as a vector single, and a matrix single. And then within my code, I can instance the vectors like this. So I can say v1 is, and then I can give it the values for the vector. So we'll say 0.254, 0.567, 0.8, and so on. I can do the same with v2. So let's put the same values in for v2. Or actually, let's create a matrix. So we'll create a matrix using the same syntax. Now, matrix has multiple columns and rows. So I'm going to do this row by row, 0.5, 0.6, and 0.7 as an example, and then we'll do 0.2, I don't know why I can't type today, 0.2, 0.3, and 0.4. Okay, so that's my matrix and my vector, and I can easily do operations on them, such as we can take the matrix and multiply it by a vector, and if you multiply a matrix by a vector, of course you get a vector as a result. And then I can simply do, for example, let's do rightlen v2 to string, so it'll write the result out. Okay, let's go ahead and run this project. Okay, and allowing time for initialization, there we get the result. This vector is the input vector that I gave multiplied by the matrix. So I have a convenient syntax here for working with vectors and matrices. So let's go ahead and get rid of this project now. Okay, and we'll come back and take a look in my neural networking lib. Now I've renamed this to DEUD from the AI lib that you saw me working with last time. And I'm going to go ahead and open up my neural net implementation. Now I've actually moved the back propagation algorithm to another unit here, so I have a different unit for the training algorithms as for the neural net as it runs forward. So we're going to take a look at the query function here, and what you can see, as I said in the video part 7, we can run the calculation for the neural network as a simple matrix operation. So I've got here the number of layers that I'm working with in my network. I'm taking a layer, taking the weights, which is a matrix. So if we're going to take a look, type matrix. And so I'm taking that matrix and I'm multiplying it by the neurons. Then I'm taking the neurons and I'm adding a bias value. So that's giving me updated neurons. And then I'm calling the activation function, which in this case is the sigmoid activation function. So just by running through each of the layers, 1, 2 pred of count layers, 1 because the 0 layer is my input layer and therefore has no weights. So we start at layer 1. I can run through and just do the product on each of the layers to get the dot product and then assign the result from those output neurons. So that's how easy it is to write a neural network forward operation using matrices and vectors. It's a few lines of code. If we go and take a look at the backpropagation algorithm, this is similarly simple with regards with relation to the previous version that I wrote. So I'm just doing a quick check here that I actually have training data to work on, and then I'm putting the number of samples. So this is the number of samples from the training set that I want to train my network on. I'm setting a remaining samples, and then I'm doing a repeat loop on the backpropagation algorithm, decrementing the remaining samples until remaining samples is 0. So when I call this train function now, I can say train this on 6 or 7 or 100 or 1,000 samples from the training data set. Then what I'm doing is making sure that if there aren't sufficient entries in the training set for the number of samples I've requested, we just loop around. So the sample index will loop and we'll get the next sample or go back to sample 0. So effectively this code so far is just setting up a loop to call the train function multiple times. And the first thing I have to do for backpropagation, of course, is to query the network forwards so that we get an output from which we can calculate our error for the error gradient. I'm then creating a local array of adjustments, weight adjustments. So you'll remember what we do is we calculate all of the adjustments for each of the weights in each of the layers before we apply them. We don't apply them straight away because we need the original weights to continue the calculations for previous layers. So I'm creating an array there, and that is an array of matrix. So these are matrices that will be applied to the weights in order to perform the adjustment calculation. Then I'm going to enter this for loop, so this for loop right here. This loop is just going to loop backwards through the layers, starting at pred of layer count, so that's the last layer, and coming down to layer 1, remembering that layer 0 has no weights because it's the input layer. Okay, so if we're on the last layer, the output layer, we do things a little differently. If we're on the output layer, this is where we calculate our error delta, and I can do that by taking the targets, which is the samples that I'm training against, and each of these targets is an input vector, or rather a sample vector. So this is the result that we want to get as a vector, and then we subtract that from the output layer's neurons. So that's getting us the error delta of the target output that we wanted and the actual output that we got. Then I'm going to say if we have only one sample remaining, I'm going to do a little extra calculation here to get as a floating point value the total error. Now we don't do that for every iteration, and the reason is that this function is going to return the total error after it has trained on this number of samples. So there's no point calculating it for every iteration. We just want to know what the total error is after we've done our backpropagation training. Now I take the error delta and I negate it. That's part of the calculation that I showed you in the last part, and then calculate the partial derivative. And I do that by taking the neurons in this layer and calculating the derivative of their activation function. So that's the sigmoid function right there. And then to create the gradient, we take the error delta and we array multiply by the partial derivative. So that means every element in the error delta vector, we're going to multiply by each corresponding element in the partial derivative. So that's this array multiply function. Then I'm going to create a new temporary matrix, which is this widened vector. So we're taking effectively the neurons in this layer and widening that vector by the number of neurons in this layer. So what that's going to do is give me a matrix, right? So if you take a vector and you widen it, give it more columns, you get a matrix. So I'm effectively creating this temporary matrix which contains the neurons, and the reason is I'm going to do multiplication against those neurons. But you'll remember that I said that we have to transpose the matrix in the previous part. So we take our matrix of neuron values and transpose it, and then apply the gradient after it has been widened, and then multiply the whole thing by the learning rate. We're going to do an array multiplication on the pair of them there. So effectively what we get here, make sure I'm not doing something stupid here. No, okay. So what we get here is effectively that calculation that I showed you in the previous video for the output layer's error gradient and partial derivative. So we've got that. We've now calculated weight adjustments for the output layer. Now we're going to loop around and come in and calculate the weights for the remaining layers. And the calculation's only slightly different because it takes into account the layer that came before it. So what we do is we simply take the layer weights, that's the weights for the current layer, and transpose them. We create the gradient by taking those weights and multiplying it by the previous gradient. That's the gradient from the previous iteration of this loop. So that's taking into account the output layer while calculating the hidden layer adjustments. And again, we do a partial derivative, we widen the neuron matrix, and we multiply the transpose of that into the weight adjustments. And then I'm creating a temporary vector which contains the gradient and the partial derivative, and multiplying those together. So that gets us our error delta for this level, this layer. And then we're going to take that widened gradient and multiply it into the weight adjustments. So really the code for backpropagation is this loop, followed by applying the weights in this loop. So if you alter the math from the earlier linear examples that we did to working with matrices and vectors, everything becomes more logical to read, easier to implement. And that's basically what I'm trying to show you through showing this code. So let's go ahead and see how that all works by taking a look at the binary counting example. Now if I go ahead and look at the source code here, we still have our output results, which is basically going to take the output vector, the vector that we get from our neural network, and it's going to translate that into binary values, ones and zeros. It does that by rounding because the neural network's never going to give us exactly 1 or 0. It'll give us 0.98, 0.97 and so on for a 1, and it might give us 0.02 for a 0. So we round those values out to get our ones and zeros and output them to the screen. Now that procedure aside, let's take a look at what I'm doing here. So I have this neural net interface which is going to contain the implementation of our neural net. I have this training set which is just a data container. This contains input values and the targets that we're trying to attain. I then have this trainer which we're going to implement the backpropagation training algorithm, and that will be represented by this trainer. I have a tester, which I'll come back to in a moment, which generates an accuracy, which I'll also explain in just a moment. So what I'm doing here is I'm looking at this little line here is just for my logging system. This is going to log to the console anything that comes out of the AI lib as it functions. And then I have this math engine index equals 0. Now what this is, I wanted to be able to run this code on either a CPU or a GPU. And so I went ahead and implemented an OpenCL library that will allow me to run code on the GPU, and a math engine library. Now the math engine library simply provides, if I go take a look at the interface, mathengine.engine, so it provides a bunch of functions for getting information about the device that we're running on, for creating buffers of data to send into the engine, and then functions for working with that those buffers. So I can copy buffers, I can add vectors together, I can subtract vectors, I can multiply vectors and so on, and this works with engine buffers. So the vector code that I showed you, the vector matrix code that I showed you in the math lib, actually works with these data types. So if we go take a look at the double vector, for example, that's what this engine buffer is that I told you I'd come back to. So effectively, when we first assign the vector, it's going to assign this local data, and then before we perform any actions on it, addition, subtraction, and so on, it'll upload it into an engine buffer, which means uploading that data to the GPU ready to be operated on. And then if I try to read the results back out of this vector, of course it will download that data back from the GPU to the local data buffer on the CPU side and allow us to read that data out. Now the math engine has two implementations. It has an OpenCL implementation and a software, so that's a single-threaded CPU implementation. So that basically means that by selecting an implementation, I can select whether or not I'm working with the GPU or the CPU. So coming back to the binary counting example, I'm selecting index 0. Index 0 is always the software implementation. So what this is going to do is say single-threaded on the CPU, that's where we're going to run our network. Now I'm going to show you changing that in a moment, but there's a caveat that I need to cover first. So I've set up my logging and I've set up to run on the CPU. I create a neural network, so this is the simple T neural net class, and then I'm going to set the bias for each of the layers. Now the way that I'm creating this neural net is I'm still passing in an array of values here, integers. So I've got 3 neurons in my input layer, 3 in the hidden layer, and 3 in the output layer. So that's 3 vectors of 3 neurons. Automatically within the constructor here, the weights are going to be set up for connecting these 3 layers together, and they're going to be set to some random values. Then I'm going to build my training set, so this is the data that I want to train against. Now you'll remember in the previous binary counting example, I had a little loop 0 through 6, which would generate the binary values that I wanted to train against. In this case, I've put them in explicitly here. This is just because I was testing this overload of the add sample method. I could have created a loop and done it that way. But I'm passing in here, for clarity, we can see 0, 0, 0, and I'm expecting 0, 0, 1 as a result. When I pass in 0, 0, 1, I'm expecting 0, 1, 0, and so on. So this is training the network to count in binary. If I pass in a 0, I should get a 1. If I pass in a 1, I should get a 2, and so on through the network. So I'm now creating a trainer. That's the back propagation algorithm trainer. That's the implementation I just showed you for back propagation. And I'm passing in an instance of the network that I want to train and the data that I want to train it against. So that's our training set going in. I'm then setting up this tester. Now I said I'd come back and show you this. In my earlier examples, I was using the total error, to determine when we should stop training. Now the problem with that method, though it worked for our examples, is when the network is being trained, the total error will go up and down. It won't always stay constant. So when you first hit that level, that threshold that ends the training loop, that may not mean that the network is trained. It may mean that the network got lucky and produced a correct result. So what we really need is some way of testing the accuracy of the network. And that's what this tester class is. If we go take a look at the tester class, let me find the implementation here. So in my tester implementation, what I'm doing is I'm in the test method, I'm calling a loop across the testing set, and that's a separate set of data that we want to test against. And then I'm looping through that data and I'm feeding the network forward, so I'm doing a query on it. And then based on the error result, I'm summing up the error and keeping a running sum, and then dividing that sum by the training set to get a percentage of the total accuracy of the network. So effectively what I'm doing here, now I'm actually passing in the training set. In neural networks, that's actually bad practice. I really should be passing in data that this network has not seen before. So we train it on known data, and then we expect the network to actually produce results from data that it hasn't seen before, and that's how we measure its accuracy. But for this simple binary counting example, I'm just passing in the training set again as the testing set. So we'll run a test, tester.test, and convert the result, which is a floating point, to string, and that will tell us our initial accuracy, probably somewhere around 50% with random weights. Then I'm going to repeatedly train the network on the training set, and I'm telling it the number of samples in the training set, which will be 7. That's the number of iterations of training I want it to do, and then I'm doing another tester.test to get a new accuracy read to see if the network got more accurate. I'm then writing out that new accuracy to the console, and I'm finally repeating the loop until we reach an accuracy of 98.6%. So that's a pretty high accuracy. You'll remember in an earlier part I explained that a neural network will never be 100% accurate. It'll approach 100%, but will never actually be 100% accurate. So 98.6 is a good high value indicating that our network has learnt to count in binary. And then finally I'm just calling output results 7 times, each time on one of the inputs from the training set, and outputting what we actually get for that query. Okay, so Readland, when we're done, let's go ahead and run this so I can show you what this does. Oops, select the right program. Okay, so we get some initialization time, and very quickly we're spitting out accuracy values, and you can see here we've reached 98.6% accuracy, and our outputs are 1, 2, 3, 4, 5, 6, 7 for input values of 0 through 6. So our network is trained. Now let me just put in a Readland to show you that again. With the initial accuracy, if I go ahead and run this, again wait for it to initialize, and there's our initial accuracy, 59.3%. In other words, not much better than a guess at this point. The neural network doesn't know how to count. But we go ahead and run this, and now our network knows how to count. Now there's a problem. We're training this network on a single-threaded CPU implementation, and I told you that parallel implementations would be faster. But in actual fact, when I run this on the GPU, off goes the calculation, and you can probably already see it is by no means faster. In fact, it's considerably slower. At this point, we've reached 92%, around 92, 93%. Everything gets very, very slow as we try to eke out that last percentage point of accuracy. So what's going on here? Why is my GPU implementation so much slower? Well, first of all, the code isn't actually optimized at this point. There are some optimizations that I still need to put in. But more importantly, I'm running on a network with a sum total of 9 neurons. The amount of effort it takes for me to upload the data for these 9 neurons and the training data up through the PCI bus is so slow that the PCI bus actually becomes the bottleneck for this neural net implementation. So if, for example, I were to upload large image data files, then once those images are on the GPU, the actual training process would be much faster than running it CPU side. But because I'm not uploading large data sets, I'm uploading very, very small data sets, the PCI bus overhead is just too high for our GPU implementation to be performant. So that's the reason why it runs slower on GPU. I'm going to perform another experiment or two with larger data sets and with some optimizations and see just how much performance I can get from GPU processing. But until then, that's where I'm at with my code. Like I said, this is actually the last video I planned for this series. I just wanted to show you how much easier it is to implement the code in parallel using matrices and vertex math. My name's Craig Chapman, and thank you very much for watching.